Now let's move on to sorting algorithms. We need to be able to sort an unsorted array. In coding, there's a lot of different ways to do this, but for this course, we'll be looking at bubble sort, selection sort, and for HL, quick sort. The first sorting algorithm is bubble sort. Bubble sort works by repeatedly swapping adjacent elements until the array is sorted. Let's say that we want to sort this unsorted array in ascending order. So we start from the left, and we start with these two adjacent elements. So we ask ourselves, is this element greater than this element? In this case, since 13 is bigger than 8, we swap these two elements around like this. And now we look at these two adjacent elements. So is 13 greater than 35? No, so we don't swap anything. And now we look at these two. Is 35 greater than 26? Yes, so we just swap these two around like this. And then finally we look at these two. So is 35 greater than 19? Yes, so we swap these around. So now we've gone through the entire array once, and we call that a pass. But notice how the array still isn't sorted yet. So we need to repeat this pass again, starting from the left again. So again, is 8 greater than 13? No, so we leave this. Is 13 greater than 26? No, so we leave this. Is 26 greater than 19? Yes, so we swap these around. And we don't have to do this one anymore because we already know that this will be greater than anything beforehand. So now we've completed another pass, so let's try again. So is 8 greater than 13? Nope. Is 13 greater than 19? Nope. Is 19 greater than 26? Nope. And is 26 greater than 35? Nope. So if we've answered no to every single comparison in a pass, that means that the array is completely sorted. And that's evident here because it is sorted, 8, 13, 19, 26, and 35. This is the algorithm for a bubble sort in Java. The function takes in a single array, r, as an argument, and will return the sorted array. If this algorithm looks tedious right now, don't worry. This algorithm does exactly what we described just now, so try matching up what I say here with a visualization of the bubble sort we went through just now. We first define n as the length of the array. Now, we define the number of passes through the array as n minus 1 inside of this for loop. We then define a Boolean variable, swap. This will determine if during a pass through the array we have swapped at all, and you'll see why this is useful in a bit. Now, let's actually loop through the array and swap some elements. We want to loop through the array minus the elements we've swapped already. So we'll go through this loop until n minus 1 minus I. The I here will ensure that we don't loop through the already sorted elements. Now, since j starts from 0, we can access the first two elements in the array with rj and rj plus 1. We now compare these values, and if rj is bigger, we swap the two elements with this code over here, and then set the swap variable to true. This repeats for every adjacent element from left to right until the loop terminates. So elements 1 and 2, elements 2 and 3, elements 3 and 4, and so on. Once the loop has reached the end, that's one pass complete. If there were no swaps in that pass, then this swap variable would still be false. So if that's the case, we tell the loop to stop entirely, finishing the algorithm. This is because in this case, we know that the sorting has finished, as there were no swaps in that pass. Finally, after everything's done, we return the sorted array here. Now when we sort this example array over here and run the program, we can see it is now sorted. The time complexity of bubble sort is O(n) squared, meaning that in the worst case, for an input array of size n, a total of n squared iterations need to be performed. And the reason for that is because of this nested for loop. And the space complexity stays at O(1), as the defined variables are constant for any array of size n. A second method of sorting is selection sort. Selection sort isn't just mindless swapping between elements like bubble sort. Instead, it chooses beforehand the maximum or minimum value, then makes a swap. Let's understand this using a descending order example this time. In this example array, we see that 35 is the maximum value, and since the maximum number needs to be at the very left in descending order, we need to put 35 at this leftmost spot. But 35 isn't at the front of the array as it should be right now. So now, we swap it with the element at the leftmost side. So we swap these two around, like this. And that's one pass through the array. Now, we find the next maximum, 26. This is also not at the front, so we swap it with this next element over here. So we just do that. And now we keep going. So in this little subarray, 19 is the maximum, but this is also not at the leftmost side. So we just swap this like this. And then lastly, 13 isn't where it should be, so these are swapped. And there we go. That's descending order right there. This is the algorithm for selection sort, also taking in a single array R. This time, we wrote our algorithm to sort in descending order. We define n to be the length of the array again. Then, we define the number of passes through the array as n minus 1 in this for loop, just like we did for bubble sort. Now for each pass, we define two variables, max num and max index. Then we loop through the array again from I to n. The reason we do I to n is because after each pass, we want to ignore the element in the array that's already been sorted. With this code over here, we find the maximum value for the unsorted elements and store its index into max index. Now that we found the maximum value, we just need to swap the leftmost element with the maximum value with this code over here. That completes one pass. We've now put the largest value to the far left. This repeats until the full array is sorted, and we finish by returning this sorted array. Now if we input this example array into the function and print it, we get a successful descending order array. Now if we wanted to do ascending order, we would need to change the code so that it finds the minimum value each pass and swaps it with the leftmost element. The time complexity of selection sort is also O of n squared. And again, that's because of this nested for loop over here. And the space complexity stays at O of 1. So when would you use bubble sort versus selection sort? Well, to be honest, both are actually really inefficient in the world of sorting algorithms. Their time complexities of O of n squared make them terrible at sorting large datasets. But they do have some specific advantages over each other. Bubble sort is good at sorting almost sorted datasets. It can know preemptively when an array is sorted thanks to the swap Boolean variable. Selection sort is good because of the reduced amount of swaps in a very unsorted dataset. Remember, to execute a swap, we have to execute these 3 lines every single time. And also, these use space due to the temporary variable temp. So in cases where writing to new variables is computationally expensive, selection sort can beat bubble sort in efficiency.